All right, this lesson is intended to get you up to speed on the Bernoulli and the binomial distributions. Let me share my OneNote with you guys, and so we can see what's going on here with the Bernoulli and binomial distribution. So first of all, let's define what a Bernoulli random variable is, or distribution. So it's any random variable whose possible values are a 0 or a 1. And I guess I should have wrote this the other way, because the failure in general represents the 0, and the success in general represents the 1. So that's the way you'll see it most of the time. So go ahead and let's define a random variable x. So the random variable x is, let's assume that it's Bernoulli with a p probability of success. So p represents the probability of success. And we can write the PMF, the probability mass function, simply by just saying, okay, well, if this is x, what's the support for the distribution? Remember, it goes up here where it can only have a 0 or a 1. The support becomes very simple. It's either a 0 or a 1, and the p of x slash, which is equal to, I'm going to always write at least I'll try to remember to always write the probability statement. So this probability that x is equal to this particular small x here is just, in this case, if the probability of getting a success is p, well then that's easy. We can simply write p in here for that. And then if I can only have two things, well then this obviously must be 1 minus p. Because I can either have a 1 or a 0. So if my probability of getting a 1 is a p, then we have to have the rest of the probability has a lie underneath the 0. Okay, so the next thing that we want to find is the expected value of this. And what is the expected value of a random variable x that has a Bernoulli with p? So it's just, if we're going to do exactly the same thing that we did before, where it's the sum over x of x times p of x, which in this case is 0 times 1 minus p plus 1 times p, which we know is simply p, because this guy goes away, it has a 0 in it, and then 1 times p is p. Very simple. And then if we're going to end up using the shortcut formula, which I claimed last time that the shortcut formula is pretty important, then we're going to do the exact same thing. So we're going to sum over x, x squared times p of x, which is 0 squared 1 plus p plus 1 squared times p, just gives us p. And here, let me just write the shortcut formula in case you don't remember it. So shortcut formula for the variance of x was the expected value of x squared, which is what we just calculated here, minus the expected value of x quantity squared, which is what we just calculated here. So we just got to square that term and put it in here. So the variance of our random variable x, if it's Bernoulli with a p probability of success, is just simply p, not squared yet, and then p squared, because we got to put the p into here. So we put a p into this thing, and we put a p into this thing, and we get p minus p squared. So I got p squared here, which is just simply a better way of writing it. I shouldn't say simply. The better way of writing it is just take a p out, and this is what you'll see many of the times, p times 1 minus p, or p times q. A lot of times people use this 1 minus p to be q. All right, so let's just use an example. Let's don't go to the example yet. Let's define, here, let me move this down, and let's define what a binomial distribution is. So I'm going to go and make this big so you guys can see it. So a binomial random variable or distribution is, and then we put the parameters with it. So I don't know if I've shown you yet, but this is our first name distribution, and it has 1 parameter with it. The binomial distribution is going to have 2. It's going to have n and P, and we're going to talk about what N and P are here in a second. So what a Bernoulli distribution is the sum of N Bernoulli trials. So what is a Bernoulli trial? Well, you do an experiment and you either get a success or failure. So a binomial is N of those, the N of those individual trials. It must have the following 4 Okay. So what are the following 4 conditions? Well, 1, the experiment must have trial. Second one, each trial must be a success, 1 or failure. The third thing is the trials are independent. And the fourth thing is the probability of success in other words, you can't change the probability of success from trial to trial and expect it to be a binomial distribution. Okay, so the binomial distribution, binomial distribution is about the probability of getting X successes out of trial. Okay, so that's what it does, and let's just go ahead and go to the example here. I think I can decrease, there you go, I'm going to decrease the amount of space. And now, so the example here was LeBron James makes about 75% of his free throws in his career. We're going to assume that that's a true statement and that he stays making that 75%. I guess that's and it's constant. If at the end of a Lakers game, one of the Lakers games, LeBron is going to take all of the foul shots, and we're going to let it be 4 because I just don't want it to get unwieldy. What is the probability mass function? So what is the PMF for his free throw percentage over the next 4 shots? So in other words, does he make 0? Oh, I guess we can go ahead and start defining our random variables. So I'm going to define this first random variable as the number. So the number out of the next 4 shots that LeBron makes. Okay, so he can make, well, we'll talk about the support here in a second. So it's binomial. So N, there's 4 shots, and he has a 0.75 chance of success. So the support for this guy is what? Well, he can make a 0, right? So it's possible that he doesn't make any of them. He can make 1, 2, 3, or 4. Support for X. So we need a probability mass that puts however much probability sits at 0, 1, 2, 3, 4. If these things that we're saying is true. In other words, it's a binomial distribution. The P is constant, and all these things sort of go down or are correct. So in order to do that, let's go ahead and just list out all the possibilities, and hopefully we can see some sort of pattern that forms, right? So let's list all possibilities over the next 4 shots. So he could make all 4 of them. So he could do success, 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 success. So makes all 4. makes all 4 shots. And so what that would look like is the probability that X is equal to 4, and that would be 4 choose 4.75. Why is it 0.75? Because that's my probability of success. And these are independent trials, so I got 0.75 times 0.75 times 0.75, so there's 4 of those suckers. And then in P, 1 minus P, the probability of failure, there would be 0 of those because we're going to get all of those. So that would be my first. So I'm going to go ahead and put a little box around this. I'm going to make it a little black box here. And then let's keep it black for all the possibilities. And then there's this possibility that he only makes 3 of them. So it's possible that he could have missed the last one. He could have missed he could have missed the second to last one, the second one, or the first one. So makes 3 shots, 3 free throws. So I'm going to go ahead and put a little box around these because this represents 3 of them. And we'll make the box the same size as the first one. And then that's the probability that the random variable X is equal to 3. Okay, so you may not have figured out why I was doing this 4 choose 4 because it's just 1. But now look what we got. I got 4 choose 3 S's, right? Because 1, 2, 3, I have 3 different. So how many different combinations do we have of that? So it's always 4, or I shouldn't say always. It's 4, meaning the number of slots that you have and the number of successes in here. And if you use that as your notation, then we know, so coming down from here, instead of having 4 of those, I have 3 of them. And 0.25, I have 1 of those. So each one of these has 3 0.75s and 1.25. 1, 2, 3 0.75s, and then 1.25, and so on and so forth. So, and this is the number of those. So this one would be 0.75, so this would be 0.75 to the third times 0.25 to the first, and then plus 0.75 to the third, 0.25 to the first, plus 0.75 to the third times 0.25 to the first, and then this is the same exact to the first. But I have 1, 2, 3, 4 of those, which ends up being that. So let's remember what this looks like. So it's 4 factorial over 3 factorial, right? So you start off with that, and then the other one is 4 minus 3 factorial, the other factorial that goes along with this. And this ends up being 4 times 3 times 2 times 1 over 3 times 2 times 1 times 1. 4 minus 3 is what's 1 factorial, which is 1. So these 3 all cancel off, and it just leaves you with 4. So that's where you're getting the 4 from. And we see that this pattern sort of works all the time. Let's go ahead and scroll up so that we can do the next one. So this would be makes 3 free throws. How about if you made 2 free throws? We'll start off with 2 successes and 2 failures. And then what I'm doing here is this is just how I'm going to do this. Obviously, you can do it any way you want to, but I'm going to take an S here and then 1 S, and I'm going to filter it through these other 2, right? So I'm going to say S. So I'm going to bring the other S over and say this is F, S, F, and then I'm going to bring it to the end. So it's S, F, F, S. Now I don't have anything else to do here, so I'm going to trade out. I have an F here, and then that just means we have an S, S, F, and now I'm going to do the same thing. I'm going to take the F and put it back here, and then put it back there. So we get F, S, F, S, and then bring it to the second spot, and you get F, F, S, S. And I believe after you do that, you have all of the possibilities. So go ahead and put a box around it and then describe what we just did. So in this particular case, what we're talking about is makes. So makes 2 free throws. And what's the probability there associated with it? It's the probability that X is equal to 4 choose 2 0.75 squared 0.25 squared, right? Because we have, for each one of these, we have 2 successes and 2 failures. 2 successes, 2 failures. So that's where you get these probabilities. And then 4 choose 2, just to rehash this, 4 choose 2 is equal to 4 factorial over 2 factorial, right? So just bringing that one over, and then 4 minus 2 factorial. So this is the combination business. And then 4 times 3 times 2 times 1 over 2 times 1, 2 times 1. So those 2 cancel off, and it just leaves you with 12 over 2, which is 6. And let's make sure we get 1, 2, 3, 4, 5, 6. So that all makes sense. Okay, so this is the probability. This one's the probability. And this one's the probability. So we're getting those mass functions that we want. And then what would it look like if we only made 1 free throw? So let's go ahead and say that you miss them all except for the last one, and then bring that S through all the other options. F, S, F, F, and then S, F, F, F. Okay, let me get the green pen, put a box around this one. And this is makes 1 free throw. So the probability that X is equal to 1 equals 4 choose 1, 0.75 to the, how many S's do I have? 1, so I only have 1, and then 0.25 to the 3. Okay, so I'll do this one more time. 4 factorial divided by 1 factorial over 4 minus 1 factorial equals 4 times 3 times 2 times 1 divided by 3 times 2 times 1, because this is 3, so 3 factorial. 1 factorial is just 1, and those cancel off, and we're left with 4. And so we got 1, 2, 3, 4, which makes sense. Okay, so this is my PMF for X is equal to 1. And then the last one is straightforward, right? So it's just one of these. So F, 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 F. And then what would that probability look like? Probability that X is equal to 0 is simply 4. There's no S's in here, so 4 choose 0 times 0.75 to the 0, 0.25 to the 4th. So it ends up being that guy, because this is equal to 1. Because it'd be 4 factorial over 4 factorial, which would be 1. Okay. Now that we have every single one of these and what it would come, or what the numbers come out to, let's write a PMF, a little chart here like we're used to doing, or at least we did last time. And so I'm going to need a lot of space to do this. So this is my small x here. So this is P of x. So in other words, this would be P of 0. And this would be my probability statement is the random variable x is equal to my small x. And this would be 0, 1, 2, 3, 4. And the support for the distribution is here. Let's recall that. It's the support. So we know all the probability mass must lie within here, underneath one of these 5 numbers. So right here, I got 4 choose 0. So 4 choose 0, 0.75 to the 0.25 to the 4. Okay, the next one would be 4, choose 1. 0.75 to the 1.25 to the 3. And we'll just keep going. And all I'm doing is I'm filling in the ones that we've already done. I'm just doing it sort of in reverse because I think we started at 4 and we worked our way backwards, but now we're going the other way. So this would be to the third, 0.25 to the 1, and then finally 4, choose 4, 0.75 to the 4th, 0.25 to the 0. Okay. Now at this point I would want to go to R to show you guys what this looks like, but we'll do that in another video. When I do all the R stuff, I'll do this part in the R video as well. But in general, what does that turn out to be? So in general, this turns out to be if X is, so I don't want to use 4 and 0.75 anymore. I'm going to use just a binomial distribution with an N and a P. So if that is the case, then what is the probability that my random variable X is equal to some small x? Now let's sort of look at what happened. Okay, so this one was 0. Look at where the X is located. That's a 1, the X is down here. That's 2, the X is down there. And the X is also on the probability of success. Okay, so I think we can redo that. And what is this number that came up here on the 4? That 4 was there for every single one of these. That was their N. In this case, we had 4 free throws. And then the X ended up right there. And then the probability of success ended up being the thing that with the 0.75, it was always right there. And then we took that to the X power. And then what did this 0.25 represent? Well, it was the other part. In other words, if it's a Bernoulli trial, you're either a success, a 1, or a 0. So this was the 1 minus P. And then how did we get the 4, the 3, the 2, the 1? Here on the 1 minus P, it was just N minus X. So you took 4 minus X being 0, you get 4, 3 minus 1. So these two numbers here must add up to N. 1 plus 3 is 4, 2 plus 2 is 4, 3 plus 1, and so on and so forth. Okay, so that's our in general formula for the probability. The next thing that we might be concerned with is what is our expected value. So our expected value of a random variable X that is a binomial distribution. So what is that? That's the question. But what we have to remember is that X was the sum of some Bernoulli trials, n Bernoulli trials. Y1, so we got Y1 plus Y2 plus ... all the way till we get to N, where Y sub I is a Bernoulli with a probability of success of P. So if I'm trying to find the expected value of X, and we remember this part, well then last class we learned that I can just take my expected value of Y1 plus Y2 plus Yn, and we can just linear operator on each one of these, so I can find the expected value of Y1, expected value of Y2, all the way to Yn. Well, we found this already. At the beginning of the lesson, we found out that my Bernoulli trials, if you come back over here, my expected value of a Bernoulli trial is just P. So I can, and then don't forget this one right here, the variance is P times 1 minus P, because we're going to use that here in a second as well. But we can come back here and go, well, this guy must be P plus another P plus all of them. And how many of these do we have? Well, there's N of them. So the simple idea here is N times each one of these. I'm sorry, N times P, because there's P of them. So this would just be NP. And that would be our expected value of X. And then the next thing is our variance of X would equal to the variance of Y1, variance of Y2, variance of Yn, which would equal to P times 1 minus. I said minus, but I wrote plus. 1 minus P plus P times 1 minus P plus P times 1 minus P. And how many of those are there? There's N. So it's equal to N times P times 1 minus P. All right, that's all I got for this lesson. Hope you got caught back up with the Bernoulli and the binomial distribution. We will do another distribution next. So the next one we talk about is the continuous.